Okay, we're back in section 8.2, doing an example now, seeing how to do a theory-based method for multiple proportions inference. The example we've got is sham acupuncture, and the study that they did was, it was a randomized experiment exploring the effectiveness of acupuncture for chronic lower back pain, okay? So what they did was they had 3 treatment groups. All right, that's our multiple proportions here. So we got 3 groups. One was a traditional, genuine acupuncture. One was sort of a sham acupuncture where they just kind of stuck needles in random places in the back, but wasn't like targeted with the actual, traditional places where it was supposed to go. And then there was some sort of traditional treatment, which was non-acupuncture physical therapy. And then the question was, did they improve or not improve in their lower back pain? So you can see what kind of data we're getting here. So that explanatory variable is the kind of acupuncture they had. There was 3 choices: the real acupuncture, the sham acupuncture, or the physical therapy. And then the response variable is, was there a substantial reduction in back pain or not? And that's a yes or no, right? Yes, it improved. No, it didn't. So that's a categorical variable. We're getting yes, no data, so we're going to get proportions here, but we'll get proportions for each group, right? Each patient had 10 sessions, and they took over 1,000 patients and randomly assigned them to one of the 3 groups. So this is a good size sample, good size study, and it was randomized. So if we find a difference here, then that will be able to be a cause and effect because we've got random assignment. All right, so the only reason there could be a difference if we observe a difference would be due to the explanatory variable, because everything else was the same. Okay, so let's set it up now, our hypothesis statements. So pi is going to be the true population proportion of people who get a reduction in back pain after getting a treatment. So pi real would be the proportion who have substantial reduction in back pain after 10 treatments of real acupuncture. Pi sham would be the true proportion of people who would get a substantial reduction in back pain after getting the fake acupuncture. And then pi none would be the true population proportion of people who get reduction in back pain if they have no treatment, or I think some sort of physical therapy they did. And they usually like to do something rather than just nothing, so that they're not comparing it to doing nothing, but they're doing it to some, physical therapy or something like that. All right, and then the alternative would be that, so the null hypothesis is that all these proportions are the same. If these 3 treatments are the same, then their proportion of success rate would be the same, right? The alternative is that not all the proportions are the same, or at least one of them is different. Okay, so let's go to the data then. You see we had about 387, 88 people in each category. For those who got real acupuncture, 47% improved. The sham acupuncture, 44% improved. And then non-acupuncture treatment, 27% improved. So some people improved in each group, but the proportions that improved were not the same. So we've got some evidence of a difference between the 3 treatments, right? This group is not equal to that proportion and that proportion and that proportion, not the same. The question for us, though, is, of course, if you randomly do a study, the proportions in the sample are going to be different. We want to know, are the true population proportions the same? And so is the p-hats that we get here different enough to conclude that the true proportions they're coming from are actually different? All right, and so what we're going to do is well, we're going to start with the simulation-based test, but then we'll see a theory-based test sort of on top of it. And to do that, we're going to jump over to the applet. So we're going to go down to, we're in chapter 8 here, acupuncture. We're going to copy this data. And then we're going to go to the multiple proportions applet. And in there, we can clear this out and we can paste in the data that we have. So what you can see is this person got the real acupuncture and they improved. This person got the real acupuncture and didn't improve. Sham acupuncture, no acupuncture, etc. Right? So the data is there. When you click Use Data, it makes the segmented bar graphs for you. And then when we do this Show Shuffle options, what that allows us to do is to simulate what would happen if we just took these 1,162 people and just randomly dealt them into two piles. Some got better, some didn't. Well, what we can do, we could use the MAD statistic, but we're going to use the chi-squared statistic because that's the theory-based statistic. Okay, it computes the value of it, 38. Apparently that's how much different these are from each other, a value of 38. And then what we want to see is when we randomly deal them out into a random way and we plot the chi-squared statistic, are we getting something like 38, like what we got in our data? Or are we getting numbers smaller than 38? And why don't we just shuffle this like 100 times? And you'll notice we get that boot kind of shape with the skew right on it. And there we go. And what was our statistic? So by random chance, you could get a chi-square of 3 or 6 or 9 or 0.2. Lots of different numbers show up. But in our data, we actually had 38.054. So let's see where 38.054 is. Count it up. Ooh, that's way in the tail. So you cannot, if the pies are actually the same, you would not get data that's this far different from each other, because our data was at 38.05, and then normally you'd only get out to maybe 9 at the most. So the p-value is 0 here, which is very strong evidence that there must be a difference, not just in the data, but a difference in the true proportions. These proportions must be different from each other. These proportions must be different from each other if we got data that was this far different. And the way we know the data was that far different was because the chi-squared statistic was so large, it was way out in the tail here. Okay? And if you click this Show Table button here, that takes your data here and makes a little table for you. If you show this little button here, it will do the p-value for you without doing the simulation. So this is really doing a theory-based test right here. It gives you the chi-square statistic and it gives you the p-value. Okay? Or you can get the p-value from doing a simulation. So a theory-based test would be using sort of this little button right here that tells you what the p-value is. And I think if we click this overlay chi-squared distribution, that will graph the theoretical chi-squared distribution on top of the simulated one and give you a theoretical based p-value, which in this case is the same as the simulated based p-value, but it might be slightly different if our statistic wasn't so far into the tail. All right. So this is kind of just re-seeing what we had. We had the p-value of 0. Yeah, there's nothing as large as that chi-squared statistic. You could do it with the MAD statistic, you get the same thing. So we've got very strong evidence against the null. There must be some difference in the three pies. Now, you might wonder to yourself, well, if they're different, which ones are different? And that's what you can do after you find evidence of an association. So if you have evidence that at least one of these are different, then you can follow up with pairwise confidence intervals. If you're certain that not all pies are the same, then some of them must be different. And if I jump back to the applet here, this little button here will create 95% confidence intervals for the difference in proportions for each group. So it will compare pi sham to pi real, pi none to pi real, and pi sham to pi none. It will compare each possible set of pies. And what we see here is that if we were comparing the real pi to the sham pi, we do see that 0 is in that confidence interval. So we don't have evidence, and you can kind of see that here, we don't have evidence that pi real and pi sham are different. They could be different, but we don't have enough evidence because they weren't far enough away. So we see that the difference between those is probably between 0.03 and 0.10. So real acupuncture is somewhere between, 3 percentage points worse or 10 percentage points better than sham acupuncture. But what we do see here is a difference between the sham and the none. So pi real minus pi none. So real acupuncture is better than none acupuncture by somewhere between 13 and 26%. So the proportion of people who found improvement in the lower back pain after getting real acupuncture is somewhere between 0.13 and 0.26. That proportion is 0.13 to 0.26 higher than the proportion of people who get no acupuncture and see back pain. And actually what's interesting is the sham acupuncture apparently is also better than the no acupuncture in this case. The proportion of people who improve after sham acupuncture is 0.10 to 0.23 higher than pi for no acupuncture. Okay, so those are the confidence intervals for the difference in the proportions. And you would only want to follow up with these if you found a significant difference. So that's why we followed up with the confidence intervals. All right, and then, so that's what this slide is showing, the same calculation. So we do have evidence that the proportion of people with pain reduction is lower for no acupuncture treatment than for the other two. All right, one last thing. So that's sort of where you would conclude, and then you could talk about, generalization. Well, this study was done in Germany. Does it generalize? What kind of back pain was it? That kind of thing. I want to show you one last thing. So if you wanted to put in your own data, let's say you had your own data, but you didn't have it in this format here, you can use the use table if the data is entered in a use table format. So what you could do is sort of copy, they have this table down here for you already. You could copy this, clear this out, paste that in, and you don't want the total, but you would need the variable name. So you could call this cow and chicken and goose if you wanted, and then change the numbers to be 45 and 62 and whatever numbers you want. Make this yes, no, and then if you click use table, then it will turn cow, chicken, and goose yes, no into the data you wanted. So if the data wasn't formatted this way, you can sort of use the table, you can sort of copy this table. You need to get rid of that, but you can sort of use that little bit of the table, paste it in, get rid of that, and just have your 3 variable names, yes, no, and then your 6 numbers, and click use table, and it will sort of do it for you that way. So that's one little thing that's nice to have. All right, so that's the end of example 8.2. You should be able to do inference using the chi-squared test, the theory-based test, and you can see that it does a simulation, but it also does it using theory-based, where it just gives you the p-value, and then you can make your conclusions, follow up confidence intervals, and there. So you should be all set.